Continuing off from our last video, we covered collisions. Let's now have a couple of examples concerning collisions. Let's have sample problem number 3. You have two identical billiard balls, A and B, are moving as shown in the figure. So A and B. A is moving in this direction, 45 degrees with respect to the horizontal, at 3 meters per second. And B is moving towards negative x, 5 meters per second. The balls collide. After the collision, ball B travels back the way it came at a speed of 2 meters per second. What is the speed of ball A after the collision? So ball A, traveling in that direction, angle 45 degrees. So let theta be 45 degrees. And the speed of A is 3 meters per second. That's basically the speed of A right before the collision, 3 meters per second. So VA initial is equal to 3 meters per second. So note, no bar over the variable. So this is magnitude of the velocity. And B is moving towards negative x at 5 meters per second. So that's the speed of ball B right before the collision. So VBI is equal to 5 meters per second. The balls are identical. So A is basically identical to B. So they have the same mass. MA is equal to MB. Let that just be equal to M. Identical, so they also have the same size and so on. Now, after the collision, so they hit each other. After the collision, the problem tells us that ball B travels back the way it came. So it's going in that direction. Now it's traveling back the way it came at a speed of 2 meters per second. So after the collision, 2 meters per second, that's the final speed of ball B. VB final is 2 meters per second. And we are looking for final speed of ball A, speed of A after the collision. So this is collision, momentum is conserved, initial momentum is equal to final momentum. So initial case, you have two objects, initial momentum of object A, MAVA initial. This time, VA initial is now velocity. We now have to take into consideration the direction of the velocity in the analysis, plus initial momentum of ball B, that's MBVBI. So that's initial momentum of the system, equal to the final momentum of the system right after the collision. We don't know the speed of A after the collision or the direction that it will go. So let that just be VA final. So MAVA final. And we'll have to look for VA final. Plus final momentum of ball B. Ball B has a speed of 2 meters per second going in this direction towards positive x. So, MBVB final. Initial momentum is equal to final momentum. Since MA is equal to MB, we can cancel out the mass, leaving us with VA initial plus VB initial is equal to VA final plus VB final. This is the equation that we will now analyze. Vector equation. So we use our component method, starting with x component. X component of VA initial. VA initial is 3 meters per second heading in this direction. So 3 meters per second heading in this direction. It has a horizontal component and a vertical component. The horizontal component is heading towards positive x direction, adjacent to 45 degrees. So we get plus or positive VAI cosine theta, where theta is 45 degrees. X component of VB initial, horizontal heading towards negative x direction. So minus VB initial is equal to VA final. We don't know, as mentioned earlier, we don't know the magnitude and direction of VA final. We are looking for VA final. So let the x component of VA final simply be VAFX. Then VB final velocity of V is heading towards positive x direction, magnitude of 2 meters per second. So horizontal, so simply plus VB final. We are looking for VA final x component of VA final. So isolate VA final x, VAFX, is equal to VA initial cosine theta minus VB initial minus VB final. Plotting in the values, we are able to calculate VA final x to be equal to negative 4.878679656 meters per second. Doing the same for the y component, we get VA initial sine theta plus 0 is equal to VA final y is equal to 0. We'll recall that we mentioned earlier, you have the horizontal component and vertical component of initial velocity of A. Vertical component is positive direction, opposite to angle theta. That's why we use sine theta and positive direction. VB initial, okay, VB initial is horizontal, no y component, and VB final, okay, VB final is horizontal positive direction. That's why we have no component for no y component for VB initial, no y component for VB final. They are both horizontal. And for VA final, we simply let it be equal to VA final x, y rather. We don't know the y component. We don't know the direction of VA final. We don't know magnitude. We are looking for VA final. So isolating VA final, we have VA final is equal to VA initial sine theta. Plotting in the values, we are able to calculate VA final to be 2.121320344 meters per second. Knowing the x component and the y component of VA final, we can use Pythagorean theorem to determine the magnitude of VA final, 5.31991684 meters per second. Magnitude of VA final, this is the speed of the ball of ball A after the collision. VA final is equal to 5.320 meters per second. And now we have sample problem number 4. A 1,500 kilogram car is involved in a head-on collision with a 4,000 kilogram truck. The two stick together and are at rest after the collision. If the truck was moving with a speed of 5 meters per second, what was the speed of the car? So mass of the car, 1,500 kilogram, whereas mass of the truck is 4,000 kilograms. So M car, M truck, M car 1,500 kilograms, M truck 4,000 kilograms. The problem tells us that after the collision, the two stick together and are at rest. So V car final and V truck final are the same. They stick together. So let that just be V final and equal to 0 because they are at rest after the collision. The problem tells us that initially the speed of the truck is 5 meters per second. So V truck initial is equal to 5 meters per second. We are looking for the initial speed of the car. V car initial we are looking for. So before the collision, right before the collision, you have the car. Say the car was initially heading to the right. We don't know at what speed. That's what we are looking for. And then you have the truck initially moving at 5 meters per second, heading towards negative x direction, heading to the left. So note, the problem does not mention a specific direction for the initial motions of the car and the truck. We are simply assuming them in this illustration, in this figure. After the collision, the two stick together and are at rest. So they have the same speed, V final, and are at rest equal to 0. Momentum is conserved regardless of the type of collision. The two objects stick together after collision. So this is an example of perfectly inelastic collision. The momentum is conserved regardless of the collision type. So you have initial momentum is equal to final momentum. We have two objects again, the car and the truck. So initial case, initial final momentum is comprised of two parts. Initial momentum of the car plus initial momentum of the truck. M car, V car initial plus M truck, V truck initial. And the same goes for the final case. You have two objects, so it's comprised of two parts. Final momentum of the car plus final momentum of the truck. M car, V car final plus M truck, V truck final. Final speed of the truck and the car is equal to 0. That means the final velocity of the car and the truck is 0. So MV car final is 0. M truck V truck final is also equal to 0. So this is the equation that we are analyzing. M car, V car initial plus M truck, V truck initial is equal to 0. Once again, this is a vector quantity, so we use our component method to analyze the equation. Looking at the diagram, all the vectors are horizontal, so no y component. we just go to the x component. X component of V car initial, we have assumed that V car initial is heading in the positive x direction. So positive M car V car initial. V truck initial, we had assumed for the two to collide. If the car is heading to the right, then the truck must be heading to the left negative direction. So minus M truck V truck initial is equal to 0. X component of 0 is still 0. We are looking for V car initial. So isolate V car initial. V car initial is equal to M truck. V truck initial divided by M car. Plot in the known values into this equation. And we are able to calculate V car initial to be 13.333 meters per second. So again, regardless of the collision that occurred, momentum is conserved. So in the first sample problem number 3, we used conservation of momentum. And for sample problem number 4, a different type of collision, but we still used conservation of momentum. So again, doesn't matter what type of collision that occurred. If you see collision in the system, use momentum analysis, use conservation of momentum. And that's it for now. In the next video, we'll go on to the last part of our discussion on impulse and momentum. In the next video, we'll talk about explosions. So once again, that's it for now, and thank you for watching.